All right, so today we're taking a deep dive into, get this, Boolean algebra.
Yeah, I know what you're thinking. Who needs another lecture on boring old math?
Right, but hold on, because this is way more exciting than it sounds. We're talking about the hidden language of computers, the very foundation of the digital age.
It all started with this guy, George Boole, back in the 19th century. A real pioneer of logic, way ahead of his time.
And we've got a mountain of research to dig through: academic papers, historical accounts, even excerpts from Boole's own writings. This guy was like the OG logician, wrestling with the big questions about how we think long before computers were even a thing.
It's remarkable, really. He didn't just think about these philosophical questions. He actually developed a system to represent thought using the language of algebra.
Okay, now you've got my attention. How do you even begin to turn thoughts into equations? Did he, like, invent a whole new set of mathematical symbol?
He started with familiar ones, X, Y, Z. But here's the twist. Instead of numbers, they represented classes or sets of things. Think of X representing all the dogs in the world, and Y representing, say, everything that enjoys a good belly rub.
All right, I'm with you. So x times y wouldn't be some huge number, it would be.
Exactly. It would be the overlap, the things those sets have in common, in this case, all the dogs who love belly rubs. He called this logical multiplication. And for adding sets that don't overlap, he used a special kind of addition called disjoint union.
So it basically created a whole new language for logic, but with math symbols instead of words. That's pretty wild.
And like any language, it has its own set of rules, some of which might seem a bit odd at first.
Like what? Give me an example.
Well, there's this one fundamental rule in Boole's system. X sets equal to X. Now, in regular algebra, that only makes sense if X is 0 or 1. But in Boole's world, this index law, as he called it, applies to any class.
Wait, hold on. How does that even work?
Think of it this way. If X represents all the dogs in the world, X sets means all the dogs in the world, and D, all the dogs in the world. Which, let's face it, is just the same as saying all the dogs in the world. It's like saying dog, dog. You're still just talking about a dog.
I think I'm starting to see it. It's like a logic loop, where saying the same thing twice doesn't actually change anything.
Mm.
Still, it's kind of mind-blowing.
This rule, along with his definitions for logical addition and logical multiplication, allowed Boole to translate complex logical statements into elegant algebraic equations. It was groundbreaking. He was literally doing math with thoughts.
This guy was a genius, though I'm guessing not everyone was immediately on board with his radical new system.
You're right, it wasn't all smooth sailing. Some mathematicians, especially outside of England, weren't too keen on his use of uninterpretables.
Uninterpretables. Okay, you're gonna have to explain that one.
Imagine trying to divide a pizza into 0 slices. It just doesn't make sense in the real world, right? Well, that's kind of what these uninterpretables were like in Boole's system expressions that cropped up in his calculations, but didn't seem to have a clear logical meaning, like dividing by 0.
Yeah, I can see how that would raise some eyebrows in the math world. So how did Boole defend these seemingly nonsensical parts of his system?
He argued that they were essentially just tools, temporary steps in the process of solving logical problems. He even compared them to the use of imaginary numbers in math, like the square root of -1, which also seemed pretty far out there at first.
And that turned out to be hugely important for certain areas of math, right?
Precisely. Boole's point was that as long as the beginning and end of a logical deduction made sense in the real world, the abstract steps in between didn't necessarily need to have a direct, real-world interpretation. He was focused on the big picture, creating a system that could capture the nuances of human thought.
That's a pretty bold approach. So were there any other controversies surrounding Boole's work besides these uninterpretables?
Oh, absolutely. There was this fascinating back and forth between Boole and another logician, William Stanley Jevons, about a particular rule.
Yeah.
X plus X equals X. Jevons was adamant that this rule needed to be included because it lined up better with what we now call set theory, where petit pre-play represents combining sets even if they overlap.
So in Jevons' system, adding a set to itself just results in the same set, kind of like our dog example, all dogs plus all dogs equals all dogs.
Exactly.
Yeah.
But Boole, being a bit of a traditionalist, wasn't so sure. He wanted to stick close to the familiar rules of algebra, and he worried that including Jevons' rule would lead to contradictions within his system.
So it was a clash of ideologies, really. Boole was prioritizing consistency with traditional math, even if it meant sacrificing some flexibility in how he represented logical concepts.
Exactly. He felt that aligning his system too closely with set theory, which was still in its early stages at the time, would make his work too radical for other mathematicians to accept.
It's fascinating how even brilliant minds like Boole struggled with these fundamental questions about the nature of logic and how to best express it. It's like they were explorers venturing into uncharted territory.
And those early debates were crucial for shaping the field. But it would take another visionary thinker to truly unlock the power of Boolean algebra and bring it into the modern age. Claude Shannon.
Okay, so we've got this brilliant but kind of controversial system of logic that George Boole dreamed up back in the 1800s. But how did we get from there to, like, the computers and smartphones we use every day? That's where Claude Shannon comes in, right?
Exactly. Fast forward to the 1930s, and you've got Claude Shannon, this young electrical engineering genius at MIT. He's the one who really saw the potential of Boole's work, but in a totally different light.
So what was Shannon's big aha moment?
He was studying electrical circuits and realized they were basically physical versions of Boole's logic.
Mm-hmm.
Think about it. A circuit can be either on or off, just like a logical statement could be true or false.
So a closed circuit, where electricity is flowing, would be like a true statement, and an open circuit where the flow's broken would be like a false statement.
You got it. Shannon made that connection super clear. He took Boole's logical operations and mapped them onto physical circuits. Series connections, where both switches have to be closed for the current to flow, became the physical representation of Boole's A and D, and parallel connections, where closing either switch gets the current flowing, became his OR.
Hold on, this is blowing my mind. It's
Mhm.
like Boole handed us the blueprint and Shannon figured out how to build the actual house using circuits as his building blocks.
That's a great way to put it. In his 1938 master's thesis, A Symbolic Analysis of Relay and Switching Circuits, Shannon proved that any circuit, no matter how complex, could be represented by a Boolean expression. He basically gave engineers this whole new language for designing and analyzing circuits using math.
So instead of messing around with wires and switches, just trying stuff out, engineers could actually design these complex circuits and know they'd work. It's like they went from sketching on napkins to having actual blueprints.
Exactly. And Shannon didn't stop there. He even developed a way to represent any Boolean function, no matter how complicated, using something called disjunctive normal form.
Okay, gotta admit, that one sounds a little intimidating. Can you break it down for me? What is disjunctive normal form and why is it important?
Imagine you're planning a party. Right, and you want to make a guest list. But not just any guest list. You want a foolproof system to make sure everyone who's invited can actually come. You have to think about who might be free that day, who gets along with who, the whole 9 yards.
Okay, I like where this is going. I'm a big fan of a good party analogy.
So disjunctive normal form is like that foolproof guest list, but for Boolean functions. It's a way of breaking down a complex logical statement into every single combination of inputs that would make it true.
So instead of just saying everyone who likes pizza is invited, I'd have to list out people who like pizza and soda can come, people who like pizza but not soda can come, and so on.
You got it. It's like you're covering all your bases, making sure no one who fits the criteria gets left out.
Yeah.
And when we're talking about circuits, that means you can design a circuit that gives you the output you want for every single possible input combination.
So Shannon basically took this abstract idea of logic and made it real, paving the way for, well, everything digital.
It was a game changer. His work meant that we could go from building simple circuits to these incredibly complex systems that could do practically any logical operation you could imagine, all thanks to Boolean algebra.
It's amazing how these different fields, logic, math, and electrical engineering all came together. It's like witnessing the birth of a new era.
It really was. And as we dig deeper into the legacy of Boolean algebra, we'll see how its impact goes way beyond just circuits and computers. It's literally woven into the fabric of the digital age. But first, let's take a look at a real-world example of how Shannon's ideas actually work in practice.
Okay, I'm with you so far, but I'm really eager to see this Boolean algebra in action. Can we actually take one of those logical expressions and, like, build a real circuit out of it?
You bet. In fact, one of the sources you gave me had a great example from Shannon's 1938 paper. He gives this circuit diagram, and get this, he writes out the Boolean expression that matches it. W plus X, Y plus Z, x. It's like a recipe for making a circuit.
Okay, but I'm not exactly fluent in circuit speak. What are we looking at here?
Imagine a circuit with 4 switches, and each one is represented by those letters, W, X, Y, and Z. The plus signs, those are parallel connections, and that dot, well, that's a series connection. So if the current can flow through either path, the one with W or that whole other part of the expression the circuit's on or true.
So it's like, if any of those paths are open, the electricity gets through and the light bulb lights up.
You got it. It's like those choose-your-own-adventure books, but for electricity. Depending on which switches are flipped, the current takes a different path, and boom, different outcome.
I like it. So what did Shannon do with that Boolean expression?
Well, the really cool part is he didn't just stop at writing it down.
Yeah.
He actually simplified it using the rules of Boolean algebra, just like you'd simplify an equation in, regular algebra.
So he found a way to make the circuit design better, tighter, more efficient.
Exactly. By using Boole's logic rules, he could get rid of parts of the circuit that weren't really needed. Fewer switches, simpler connections, the works. This made the circuit cheaper to build and way more reliable.
That's incredible. It's like he found a way to optimize thinking itself, at least when it comes to these circuits. This is way more important than I realized. It's not just some abstract math thing. It's the bedrock of the entire digital world.
It really makes you think, doesn't it?
Oh.
And it's not just computers and smartphones either. Boole's legacy is everywhere: digital logic, set theory, even those algorithms that power AI.
It's like this hidden language that's running everything behind the scenes. And if you know the language, you can understand how it all works.
Exactly. Every time you send a text, watch a video online, use a search engine, you're tapping into systems built on Boolean logic. It's the code beneath our digital lives.
Okay, so for anyone listening who's thinking, this is cool and all, but what does it have to do with me? Why should they care about this Boolean algebra stuff?
It's about understanding the forces that shape our world, even the invisible ones. Every click, every swipe, every search, it's all built on this foundation of logic that George Boole figured out on paper over a century ago.
Wow, yeah, it's like peeking behind the curtain and seeing how the magic trick is done, except it's not magic, it's Boolean logic.
Exactly. And who knows, maybe by understanding the system, someone listening will be inspired to create their own digital magic.
Now that's a great point. This isn't just about the past, it's about the future. It's about understanding where we came from so we can keep innovating and pushing the boundaries of what's possible.
Well, as we wrap up our deep dive into the world of Boolean algebra, any final thoughts you want to leave our listeners with?
You know, it's fascinating to me that Boole himself believed his system wasn't just a tool for, representing logic, but a way to understand how we think, how our minds work. He even thought it could be applied to things like probability and making decisions.
You're saying there's still untapped potential in his work, even after all these years.
Absolutely. I mean, every system has its limits, right? But sometimes it's by bumping up against those limits that we make the most exciting discoveries. It reminds us that the quest to understand our own minds, our capacity for logic and thought, that journey never really ends. Who knows what breakthroughs are still out there waiting to be uncovered? What an incredible thought to end on. It's like we've climbed to the top of one mountain only to realize there's a whole range out there waiting to be explored. Thanks so much for joining me on this deep dive into the incredible world of Boolean algebra. It's been a wild ride.
The pleasure was all mine.
Until next time.